Originally, so I've been out there about 9 years now, but I still feel like this is home for me. So glad you guys were willing to come out and have me at the conference. As mentioned, this is coming up here. I'm going to talk about machine learning and the blockchain. My own background and bias is I'm a machine learning guy, also a bit of a complexity theorist, so I know crypto and I know blockchain well enough, but we're going to start off from the machine learning person's perspective and talk about where the overlap is. Since we could go here. Cool. Oh, is there a clicker for me? Thank you. So to start out, I'll give you a really brief history, more of an overview on where machine learning really has come from and what the advancements have been, and then talk mostly about where is machine learning going, and specifically, what will this relationship be with the blockchain? Two very popular topics, but not topics that obviously relate to one another. For those of you who don't know, this is machine learning in 3 lines, really aimed at a programmer to understand. Get some data, label your data, fit a model. And if you're into machine learning, you want to know all about those functions. If you don't, that's as simple as it really comes down to, not to undersell what people like myself do professionally, but that's mostly it. At a more high-level point of view, we can say we take data from databases and from S3 and document stores and wherever, and they go into some sort of black box, out of which comes this solution. It's a prediction, a classification, could be just about anything. And if that's still too high level, or if I'm moving too quickly, or if we've got any more MBA executive types, here's one way you can put it. And if you want to know how to do that, we can talk afterwards, but I didn't come here to pitch. So I think about machine learning a lot sort of from like a philosophical, mathematical point of view. A lot of the core ideas have been around since the 50s or earlier. Gradient descent, the chain rules we heard about in the first talk. These are the things that we've just done on mass scale. So here we have a set of transistors that power computers through the ages, obviously shrinking. The ones we make today, I don't know if I could even put on the chart here, you wouldn't see them. So machine learning benefits from all these things. I'll pick out a few to go through. Faster compute has been one of the most obvious ones. As computers get exponentially more fast, we can do exponentially more with them in terms of machine learning. Harder problems, longer compute times to solve them. But the real winner has been parallelization. I'm sure many people have heard that we've gone from the CPU, the central processing unit, to the GPU, errantly called a graphics processing unit. Really, it's a massively parallel system that does linear algebra very quickly. And that's beneficial to machine learning people because essentially all the algorithms can be expressed that way. Deep learning relies heavily on that, as well as a lot of the other underlying algorithms. So yes, faster compute, but mostly parallelization has been a big help to machine learning in general. More data and better data are a big key to that. More data in particular, there's been a number of interesting studies that come out every so often, white papers and whatnot, where people will say, let's take the old approaches, things people were doing in the 90s, and go back to an old paper, find an algorithm that performed pretty well under certain conditions. Take the same algorithms and run them again on a corpus of data that's 10 or 100 times larger. And what's been interesting is the simpler solutions have dominated asymptotically in a lot of cases, which tells me that algorithms aren't always the key. Data is often the key. Feature engineering is a big part of that, a big challenge, something I and my team spend a lot of time on. How do we prepare the data to do things that are useful to us and find interesting insights out of them? I undersold a little bit when I said you throw the data in, the money comes out. Sometimes that's true. We see a lot of that in image recognition and certain telemetry solutions like factory data and stuff like that. But a lot of the work that goes into it is figuring out how to better represent the data in a way that an algorithm is able to consume it. Training techniques, I won't get into these just for time's sake, but there's a lot of things that ML has benefited from. I haven't listed blockchain yet, but we'll get into that. This is your basic machine learning regression, for those of you who don't know. Blue are our dots, x-axis is our one-dimensional data, y is what we're looking for, and the red line is our model. So if you have beautifully simple data like this, it's quite trivial to make a model. The unfortunate thing is data usually looks like this. It's nonlinear, it's whatever that is, that's some real data, but it doesn't matter where it comes from. You try and fit a linear model, you get an erroneous answer. So one of the many challenges I'm going to go over in the next couple slides that data scientists and machine learning practitioners face is that data has these nonlinear relationships. So simple linear approaches won't cut it, and it takes presumably some intellect or some cleverness to figure out how to model that better. Maybe that can be automated. Another one is that data is often massively highly dimensional. So two common examples are language. You could split up a document as I've done here and count the frequency of words that appear. That's a technique that was quite popular when I was in grad school. It has really been replaced by techniques like word2vec. It's still around. Essentially, think of any document. Yes, the is the most common word, but there's hundreds or thousands of words in that document. To represent each of those as a feature is one approach, but then you have a huge number of dimensions, which is a hard problem to solve mathematically. Same idea here. This is a single image from the famous MNIST handwritten data set collection that a lot of machine learning is done on. To us, this is an image, right? But to a machine, it's a matrix of numbers, and the image corresponds to the matrix on the right. Can we shove all that data in and the machine ask the machine to magically figure out what digit we're looking at? And the answer is yes. It can now do that better than human beings can do it in a lot of situations. So this multi-dimensional, highly dimensional problem was solved through a lot of clever techniques. There's still higher dimensional problems to be worked on, but this is one of the challenges data scientists face. Feature engineering, as I mentioned, expensive and hard, traditionally done by people, now being to some degree automated. You've probably seen some diagrams like this out of the deep learning literature, where we're trying to do, in this case, facial recognition. You build multiple layers of different neural networks, and the hope is that somehow in that process and through the magic of back propagation, telling it on the right end that something is or isn't a face, and on the left giving it that raw pixel color data, that this system can engineer its own features. And it does that. It does it at the earliest layers by just figuring out some of these local contrast patterns, or what I would call an edge detector. So, don't jump in and say this is a face the way our brains kind of seem to do it, but just say, hey, we seem to see lines here that connect and are meaningful. Of course, from lines, you can build up basic geometry, shapes and whatnot. From shapes, you can eventually model eyeballs and noses and mouths, and from all that, once you're that far, it's kind of an easy problem to say two faces, a nose, and a mouth in the right configuration seem to be a face. So this feature engineering thing is maybe putting a few people out of a job, as we find for certain problems. You can automate that. So everything about machine learning that I'm covering is how do we find the areas that are hard and make them easy, or make them automated? Data is big was for a long time a challenge, and sometimes bigger is better, not always, but often with data it is. So when you have more data than you can fit in your machine's memory, or even on your machine's hard drive, how do you deal with that? The answer has been data parallelism. Early on we saw Hadoop, and which obviously is still around, but Spark is really the premier technology for that amongst a number of other tools. Not to mention that I can go on Amazon Web Services or any other cloud provider and buy a massive machine like this with 128 CPUs and almost 2 terabytes of memory, which was unheard of to anyone my age when we were kind of getting first into computers. And that will continue to grow in some capacity. There's going to be some physical limit to what happens with Moore's law, but we're getting beefier machines. We're also getting bigger data sets. Yet the tooling is coming along. As I mentioned, I have the pleasure sometimes for some of my clients to go in there and spend a whole lot of their money by making a lot of these machines, running some difficult problem for a few hours and then shutting them down. That's something that would have taken a team of people in a data center and specialized engineers managing all the hardware to do just 10 years ago. Now a team of 7 or smaller, 7 of mine can do it. Data happens in real time. That was difficult for a while. Much anymore. We have Spark streaming, we have serverless architectures, we have these great tools like the Bloom filter and the count-min sketch, which are probabilistic data structures. They allow you to do things like count the unique elements you see out of a massive and unpredictable data set. If you accept a little bit of a compromise, like only being 90% accurate, or getting all the false positives, never having false positives, but accepting some false negatives, little compromises like that can allow you to process massive amounts of data in real time with a small amount of memory. So people have been clever in multiple ways, in probabilistic ways, in streaming ways, coming up with the whole idea of let's not even worry about servers, let's just have Lambda functions that do our work for us. So with all those things in mind, my life has gotten a lot easier over the last decade, and I wonder often, where is machine learning going to go? As things that I used to spend a lot of time doing are now done in automated fashion, how am I going to make money in the future? Obviously, mobile's a big area, and there's a lot of good work of getting things like TensorFlow to run its models on mobile areas. I'm not so much in that space, but I see a lot of progress. Robotics, of course, self-driving cars, and in general, tooling. So what's going to happen next? We're obviously going to get to the blockchain. I want to share one more point about this and introduce some comments about data privacy, because Obviously, this is becoming a common issue for us. I personally am against the idea of software patents. Happy to talk about that offline if you want. But I do still reserve some support for things like pharmaceutical patents. If it takes millions of dollars to come up with a treatment of a drug that's going to affect a small group of people, you have to incentivize someone to do that research. And if you spend millions of dollars and fail, that's not a great investment. So the patent protects the drug makers to, the fact that they come up with a formula like this, and that's the output of millions of dollars. Any undergraduate chemistry student could copy that. How do you protect your investment? And I'm not going to say the system's perfect or that there isn't corruption or whatever going on, but the point is you do need to protect the things you create intellectually. In my area, that could be a machine learning model. What if I train a model, I spend months acquiring data, getting the system together, and then I put that in, and at the end of it comes out a model that's pretty simple and probably fits in under 100 megabytes. Could be easily stolen by someone, and then they have all of my assets through that whole time. In fact, it gets worse. On my podcast, Data Skeptic, I interviewed this guy, Florian Tremere, about a paper he wrote, stealing machine learning models via predictive APIs. So you take some of those things, like our first speaker was talking about, the cognitive services. If you're clever about it, you can reverse engineer how that system works. And actually, you don't have a lot of incentive to do that because those systems are very affordable. You pay pennies per call, but what if I came up with some smart system and I wanted to charge people $10 per usage and that was my business? Someone like Florian or someone who read his paper could steal my assets pretty quickly with techniques like that. So can we protect our models in some way? Data is the new oil. I forget who originally said that, but it really is the unfair advantage of a lot of companies. If you think back maybe, 15 years ago, before spam filtering really worked, it was a disaster. I mean, handling your email was a major chore every day. Suddenly that fixed, and I give a lot of credit to companies like Gmail. The unfair advantage they had was everyone signed up for it en masse. So they saw not only the spam you got, but they saw trends in spam. So if you were running spam filtering for one company, you only saw things that happened at your company. They see things that happen immediately, and they get a big advantage of that. That's why spam detection is federated today. Just to pick out a fun one, Steam, the video game provider, they have analytics on user behavior and how people play games that no indie game developer would have. They will always be smarter about what's going to be a hit game and how are people going to engage with it. More practical example is Waze. I mean, the fact that a large critical mass of people has Waze installed on their machine means that they are much smarter than you are at figuring out how to navigate. That may be hard for a Chicagoan to appreciate, understanding that our system is pretty good here for moving around, and we have 2 seasons, winter and construction. But despite all of your little local knowledge and shortcuts, I think you'd be hard-pressed to beat the machines in this area now that they've been federated. And lastly, the NSA. Something wrong with the projector, I guess, but they have some data advantages as well from all the federation they do. And of course, Cambridge Analytica did some great federation, which causes us to ask questions about, opting in. So many people are now thinking, I don't want my data in your model. I want to opt out. I want to be anonymous, all these things. And in some situations, that's probably right. But what if, my phone rang after this and they said, hey, we're from this hospital, we're this research center, and those diseases that all of your relatives passed away from, we're working on those. Would you give us a blood sample? Absolutely. Why wouldn't I? I want to be in their data set and help whoever can benefit from whatever my DNA or whatever tells them. But I don't want my insurance company getting a hold of that blood sample and raising my rates because they found something negative in it. So I want to be in, but I want to be anonymous. How can I do that? And there are some people who would say, I want to give you my data, but I want something back. If you're going to go to a company like Mint, give them all your financial data, they have to give you something in return, and that's presumably some advice or some tips or forecasts or things like that, in addition to just selling you products. And this is kind of the modern world of data management and privacy in my mind. So quick note on anonymity. There's a lot of old techniques that still apply. Here's a quick survey I could ask people to take. Tell me how many of these activities you've done in the past month. I bet a lot of you are zeros. These aren't common things, but surely there's some ones in here, maybe a few twos, maybe a 3. And imagine if I asked you all to fill this out, tell me your number. Probably would. You're not really revealing much to me. If I had added a sensitive question, people would be hesitant to answer that. But there's a trick you can use. I give this survey to the left half of the room. I give this survey to the right half of the room. And I ask you to give me your number. Because I want to know about people who drive while intoxicated. Not something anyone's readily, or most people are not ready to admit if they've done it. And I won't know who did it from the survey, but if the average number over here is 2 or 1, and the average number over here is 2.2, then I've just measured how many drunk drivers are in the room without identifying them. It's anonymous. This is a simple and old technique. Much more sophisticated stuff come around. In large part, we can get to anonymity through averaging. However, as you look at this, it's sort of anonymous, but everyone sees the guy in the yellow shirt, right? Just because you're anonymous doesn't mean you don't stand out. It's not a perfect system just to aggregate and take a mean. 2 quick notes on other areas that I think are interesting but a distraction. Zero knowledge proof systems are a very cool idea. They're a way you can show someone that you've solved the problem and prove it to them without giving them the solution. This would be great if you could solve the hardest known problem in computer science and wanted to keep that to yourself, or if, I guess, hypothetically you wanted to, keep your intellectual asset private. However, I don't think these are practical anytime in the near future for some complexity reasons, but also because this conference in San Diego later in the year, pretty much the premier conference on complexity theory, has no papers in interactive proof systems. One on proof systems, but not of this nature. So interesting stuff, but probably not going to solve our privacy needs. Can we do better? And what would that even mean? Users want to keep their data private, but there's benefits from your data being in a trained model. That means it represents you. Your data is necessary to make useful models. Creators of these models, they want their model to be private because that's their intellectual property on some level, but so do the individuals who put their data in it. And even the owner, if I were to trust that hospital I was going to give my data to hypothetically, there's no guarantee that they don't get leaked, hacked, acquired, or who knows what. And especially acquisition is something that concerns me on small companies. They may come in with the best of intentions, but then get bought out, and the procurer of that company isn't necessarily going to have the same privacy concerns. The last one I want to mention, because it is a little bit of discussion related to the blockchain, is homomorphic encryption. This is the idea that you can send someone your data and it can be processed. You can send them the computation you want them to do and your data, both encrypted. They can do the computation in such a way that they get the result, but they have no idea what they computed, and send that back to you. There are some feasibility challenges around this. So this is an area of active research, but I'm not super bullish on it just yet. I don't know if it'll ever become at the scale where it's interesting for privacy questions. So I guess it's blockchain, right? That's the answer to everything these days. What are the benefits of blockchain? These are the 6 I pull out. I'm sure if there's any hardcore blockchain people in the audience, they'd want me to have this be about 100 bullet items long. For me, these are the 6. And to revisit my notes earlier on what's good about machine learning and where are the areas we need improvement to push machine learning even further, here's that list, and also kind of graying out the things that don't overlap. So what matters here? Maybe the shared ledger, that's interesting in certain ways, but really is transparency and trust. If we could somehow put data into the blockchain, everyone can see it, there's no funny business, fully traceable, that's a novel idea. I don't know quite what it means just yet, but it sounds interesting. From machine learning's point of view, there's a great opportunity for more data, people to contribute it to the chain, for it to be the central repository for tracking, all that sort of thing, and potentially for interpretability, because of course anything running on, let's say, the Ethereum VM, you can see the code even if it's somehow encrypted. So maybe there's some opportunities here. A couple of projects I want to highlight pretty quickly as we go through them. The one I'll cover most is this federated data thing, so I won't mention it here. But I would be remiss to not say OpenMind and Singularity.net belong on this list. Maybe some others I'm not aware of. And Algorithmia I'll talk about briefly. This is the company that began doing API marketplaces, so a kind of cool idea, and they've been branching out into this Danku project. The idea here is that if I have a problem to be solved, but I'm not a machine learning person, can I put that contract onto the Ethereum network, or presumably a lot of the other similar things, let people compete for that? So this could be an interesting way an entrepreneur or some ambitious students could go in, try and build that model, sort of like how Kaggle does that, but tied into the blockchain and with guaranteed contracts. So whoever gets the highest AUC or F1 score or just plain accuracy, they're going to win the prize and get the contract. There are some challenges to that, I think, financially, because you can overfit that model and win the prize, but that seems like something we could deal with perhaps. The problem I see here is to do a simple test like they did was going to cost about $300,000 for a very simple model. And that's not because they spun up some massive cluster of computers and ran on some big data set. This was a pretty typical problem that I would solve on my own machine most of the time. So while this is interesting, I'm not sure they're there yet. Much of the problem here is that all the data went onto the blockchain, and that has a cost. They're talking about ways they could pull that, the data itself out external to that. Maybe we'll get somewhere, but it's unclear. I'm going to skip this in the interest of time and get to my favorite example, which is something Google's been doing with collaborative machine learning and centralized training. So the idea here is we all have our phones, and if you're Android or even if you're on iPhone, you get some Google stuff on it. You get these recommendations that ideally would be context aware. So if I search for flowers right now, it knows I'm not home. It probably wants me to go to a walk-up florist, not to call a number and arrange something for a week from now, or restaurants for that matter, that sort of thing. So it would be great if Google could give us better recommendations, but even though that's the company that says don't be evil, we don't want to implicitly trust anyone. As a friend of mine likes to say, trust but verify. So I would like those recommendations to be better tailored for me. I want them to have my data, but I maybe don't want them to be doing other things with it. So the concept here is, can they send the modeling to my phone, let it run and retrain locally for me, and just send back parameter updates? So they never see my data, they just get back the bits that are relevant for improving the model. So very novel idea, has some challenges because of course you can reverse engineer some of that, but if there's one area that federated data has a lot of promise with machine learning, it's that one. That you accept the model to your local compute environment, you let it train there, and you give back whatever improvements you made to the model based on your data set. You have to give less trust to Google or any other company doing that, because all they're getting is model improvements, which aren't exactly your data. Still not perfect privacy, but the best of the middle ground here, where we have these computationally infeasible things like homomorphic encryption, or the Danku approach, which is prohibitively expensive. We're at a nice middle ground. So where are we going? What are the issues? The exact use cases for blockchain ML are a lot of hype. I think there's some interesting things there, but it's more around data provenance and data sharing and the potential for federated data in this way, that local training can happen and model updates can be sent back. So it's a very preliminary area, but I think it's something we're going to see a lot more papers and things coming around about. It's going to suffer from all the standard problems with blockchain technology like transaction delays, but that's nothing new. Those are things people are working on anyways. So as I mentioned, the real opportunities here I think are federated learning. What I didn't cover much of, which I call data stewardship. In that hospital example, wouldn't it be great if I had some middle person I trusted to look over my data well? And when the hospital said, we want Kyle in the study or we want his blood sample, they say, okay, you send me your code, we'll run it on his data to give you back your model, but you never get to look at his code. Those are things we could potentially do with some of these technologies. And data provenance is, for me, the real winner in blockchain, the ability to track exactly where data came from, who generated it, who's seen it, all those sorts of things. So not the greatest machine learning platform, but the fact that we can have data provenance means maybe that's our transmission and storage mechanism, and we do our machine learning in more traditional ways. I know I flew through some of that because we've got short talks today, but I wanted to save some time for questions if there were any, and happy to follow up afterwards too if you're interested in what I do. This is how you can find me online.
So is part of the problem with using the blockchain for your models the fact that it's a linked list and it's not very effective for a lot of different types of processing we'd like to do?
So the question was around, is the main challenge around using blockchain that it's more or less a linked list, and that could be the challenge and why ML is not a perfect fit? I mean, yes and no. So the dream is that the blockchain, or at least from like the Ethereum point of view, that is this massive virtual machine. You don't care where it is or how it works. You send your code there, and somehow it gets run, even more ephemerally than like serverless architecture does. That is part of the challenge because your code has to be accepted into some block and processed, but it's the same as any other person trying to do blockchain things. I think the bigger challenge is that the benefits, the cost that comes with the benefits of the anonymity don't seem to add up for the scale that's required for machine learning. Building really simple models, sure, great for that, but you can do those on a local machine. The benefits you get in distributed and federated data don't seem to yet add up, and those challenges like that become pretty insurmountable for the scale that machine learning is done at today.
There's a basic attention token browser, which is like this app that runs on top of Ethereum is kind of trying to do something like this. It incentivizes people. You essentially sell your attention. So if you use the browser, it's invented by the guy who made JavaScript. I don't know if you looked into that. It covers a lot of things that you mentioned. And it's already out. You can essentially earn some kind of cryptocurrency based on what advertisements you see.
Interesting. I'm not familiar with it. I'll look up to. The comment was about a browser plugin, I guess, where
it's called Brave. The browser is called Brave.
Brave.
And the token is called BAT, Basic Attention Token.
Gotcha, the basic attention token, which it sounds like, I guess you get paid for watching ads. So flip that model on its head. That's interesting. All right, we're out of time. Let's take one more.
So I guess in the age of quantum computing, how do you think blockchain is going to fare? And I guess the first time somebody breaks a blockchain, you think everybody abandoned?
So the question is around quantum computing in the blockchain. We're a ways out from a practical scale quantum computer. It's not clear that quantum doesn't break encryption per se. It just means that some of the encryptions we use today are much faster to process. It's just an order of magnitude change. So that's going to affect the whole world, not just the blockchain. There will be new solutions to security and privacy if and when quantum computing becomes a threat to it. So I don't think quantum is the threat to blockchain at all. Mainly because the technology is slowly coming about, and from a complexity theory point of view, it's a solvable issue. I think the challenges of blockchain are outside of quantum. Anyway, thanks everybody.
Thank you so much, Kyle. Thank you.